Hello everyone, very good evening. Welcome to the session of GATE preparation for GATE EE. And so last week we discussed uh, magnetic equivalent circuit. Okay, so we solved a couple of problems where I hope you might have gone through those problems and you are well versed with them. Okay, so first let please confirm whether am I audible or not. Anyone please confirm I am audible or not?
Yes, sir. Yes, sir.
Okay,
It's super audible.
great, great. Thanks a lot. As per the agenda, this week, today we will discuss single phase transformer equivalent circuits, and basically we will solve problems based on that because the objective of GATE exam is to check your numerical ability just than the theoretical ability. So, of course, we will focus more on numericals. So, okay, let me share the screen. I hope my screen is visible to you guys. So this is the question which is on the screen. We will try to solve those problems. Okay, so please read them very carefully. I hope you guys are aware with the equivalent circuit concepts. Why is it required and how to draw those equivalent circuits? So basically, any idea anyone can answer, or anyone who doesn't know anything about equivalent circuit also, they are encouraged to speak so that we can discuss those topics. Just we will do brush up, otherwise we will move ahead only with the numericals. Okay, so if no response, let me restart.
Sir, I think everyone has basic knowledge about transformer.
Okay,
So,
that's great, so we can
I
move
think,
ahead, right?
yes, sir.
Okay, just I don't know why this pencil is not working. No, it is fine. Yeah. So I hope you have read the problem. And so in the first part, it is asked that we have to find out the equivalent circuit of transformer referred to the low voltage side. Okay. So uh, see, transformer has two windings. I think we all agree. It is again disabled. Huh. Yeah. So when we draw any transformer, we have basically primary side resistance. Okay.
Sir, I guess this is not a gate question, sir. I think this
No,
is a conceptual
this
question.
yeah, this is conceptual question. It is five-part problem basically, and in GATE you will face such kind of problems. So you want only GATE previous year questions?
Better, that would be better, sir. I think.
Okay, so let me get those problems. But actually, our agenda was today for to discuss the conceptual questions first. So based on the basis of that, I hope you all might have some great question bank. You will be able to solve those questions. But anyway, if you say so, let me find out some gate problems.
No, sir. If you have that, I think that is also will be beneficial, sir. If everyone agrees with that, so I
Okay,
don't think.
that's why I asked in the last session also, and today I'm also asking if anyone has any suggestion, please speak up. Otherwise, I would conduct the session as per my convenience or as per I think. So please let me know what do you guys want, which questions do you want to attempt, whether get previous year problems would be beneficial or whether these conceptual questions which will eventually help you in solving those problems. So as Atanu, right? Atanu has said that get previous year question would be fine or better compared to such kind of problems. So from next session, I will pick three, four gate previous year questions. Okay. Uh, any other suggestion or comment? Okay. So let us move ahead with this problem. The timing. Yeah. So I was saying that a transformer will have a primary or an equivalent circuit which will be shown like this: primary winding resistance and leakage reactances along with core loss component resistance and magnetizing reactance. Okay, here we will supply primary voltage. Here leakage reactance XL2 for the secondary side and secondary winding resistance R2. Okay, so this is the what a standard equivalent circuit of transformer looks like. Okay. Now the thing is we have to find out all the parameters, and after finding out all the parameters, we will be able to say that these are the values of all those parameters, and then our equivalent circuit will be completed. So we have to refer to the LV side, low voltage side, right? So uh, 8000 by 277 volt. So basically, 277 volt is on the secondary side, which is LV side, right? And these excitation branch impedances are given referred to the HV side. So we have to refer first excitation branch elements to the secondary side and the primary branch elements, these elements, we have to refer to the secondary side. Okay, I hope it is clear. Now, first, let me write all those values, then we will be able to transfer to the secondary side. So this is 5 ohm, this is 6 ohm, says 50 kilo ohm, and XM is 10 kilo ohm. These parallel branch elements are in kilo. So basically, to reduce those values, whichever will go in core loss component and magnetizing component, we tried to minimize both the components for obvious reasons. Could anyone comment why do we want to minimize those excitation branch currents? And this Excel2 is,
So to reduce the magnetizing current.
yeah, That is correct because if you are able to reduce the magnetizing current, it means you are improving the power factor of your transformer.
Also, so the core losses will be reduced, sir.
Yeah, definitely. Core losses will be reduced if you are able to reduce this component of current or overall this component of current. So this component IC, core loss component, that will be a part of whatever current is flowing in parallel branch or excitation branch. So both XM to reduce this current in XM will improve the power factor of the transformer, and this core loss component current, if you are able to reduce that component, eventually you are reducing your core loss component, right?
Sir,
Yeah, go ahead.
sir, this XM they did give at the secondary site. No.
XM is given with the high voltage side, primary side. See, excitation branch impedances are given referred to the high voltage side of the transformer.
Okay, okay, sir. They right.
Uh,
Sir, I think that would be 0.005 and 0.006, sir. That R1, R1,
R1,
because that is low voltage side, right, sir? Secondary side is 277 voltage.
right.
So that would be 0.005, sir, because that is
They
low
are
voltage.
right. You are talking about R2 and XL2 as 0.005 and 0.006. See, these are secondary side parameters, okay? And these are already on the low voltage side. So that will be as it is. It's just that we have to divide it by A square on all the primary side parameters. Are you convinced?
Yes, sir.
Okay. So let us move ahead. So R2 is 0.005 ohm and XL2 is or XS is 0.006. Okay. So this XL2 and R2 are already on the low voltage side because they are secondary side parameters, right? Only the primary side parameters we are referring to the secondary side. If we are doing so, we have to divide it by turns ratio, a square of the turns ratio. Okay. So that's why I wrote it as a square. But mm, it is very confusing what is a n1 by n2, n2 by n1. Okay. So keep this concept in mind when you are referring from 1 to 2. Let us suppose 1 is the first winding, 2 is the second winding, and you are referring to 1 to 2. So write it as R1 or 1. Okay. If you are referring R1 from the primary to secondary, you have to multiply with two number of turns of the side where you are transforming. That will be N2 divided by number of turns from the side you are coming, right? So that will be N1, and you have to square it. Okay. So that will be your overall resistance referred to that side. So when here 5 ohm, which is placed on the primary winding, when you are referring this resistance 5 ohm to the secondary side, you have to do what? 5 into secondary side number of turns, that will be 277 number of turns, and basically it is voltage, but V2 by V1 is equal to N2 by N1. So that's why at the place of number of turns, I am conveniently writing the amount of voltage, okay, divided by from the side you are referring. So that is 8,000, and you have to calculate it. Okay, so that will be the value of primary resistance referred to the secondary side. Okay, so that should come out. So please calculate this value. Someone please calculate this value for me. In the meanwhile, I am referring the XP to the secondary side. So that will be XP dash. This is RP dash or it's better to call R2 dash H2 dash. So XP is 6 ohm. Okay. And again, you have to multiply with the same ratio, 277 by 8000 square. So those values we can write here. The other thing is these parallel branch impedance, right? RC and XM. So RC by A square will be basically RC2 dash I can write, and it will be 50 kilo ohm into 277 divided by 8000 square. So this value will be the value of resistance, core loss component resistance referred to the secondary side. Now magnetizing reactance referred to the secondary side will be 10 kilo ohm into 277 divided by 8000. So these all values, if you calculate, you will get as 0.006 ohm. Okay, this will be 0.0072 ohm. Core loss component will be 60 ohm, and magnetizing reactance component will be 12 ohm. Okay, now we have referred all these components to the secondary side. We have calculated. Now voltage is remaining. Okay, so voltage, to transfer this voltage towards the secondary side, again we have to do the same thing, but here this time we have to multiply with only turns ratio, not the square of turns ratio. Okay, so
G2 by A.
yeah, right. Vp dash, we can write that Vp by A, and the logic I told you that you are referring it to the secondary side, so Vp into N2 divided by the side you are coming from. So here we can write Vp was given as 8000, right? So 8000 into 277 by 8000. So eventually it will be 277. Okay. So you can see this Vp by A is coming out to be 277 volt. Is it right? 277?
Sir, it is equal to secondary side voltage.
Yeah, yeah, what I'm telling here. So because uh, after this step, if you will draw this circuit referred to secondary side, then let me draw each elements step by step. So now this resistance, which was earlier only R2, now it will be R2 dash, that is equal to R2 plus R1 into N2 by N1 square. Okay,
Sir, we are
similarly,
referring,
yeah,
sir, we are referring into the secondary side. It will remain same, na?
will remain same what?
R2 because we are referring the circuit into the secondary side.
Yeah, but secondary side resistance was earlier some value, right? See, here R2 was already 0.005. We are referring R1, right? So
Yes.
basically, I should write R2 plus R. I have written correctly only R2 plus R1 into N2 by N1 whole square. So we are referring this
Okay.
component. We are
Okay.
referring
Means
this
okay.
component. Okay, so this is all, and here no elements are present towards the primary side because we have referred it to secondary side. So it will be Vp dash, that will be Vp by A. Okay. Similarly, you can write it here x2 dash, that will be x2 plus x1 into n2 by n1 square, and here xm dash and rc dash. Okay. And hence, whatever the voltage will be on the secondary side, okay, and the voltage between primary side, if they will be loaded, then there will be some drop. Otherwise, both voltages will be same.
And sir, where we should show the induced EMF primary and secondary.
Here only. Uh, Here you can show the induced EMF of the secondary side, or this is referred to only secondary side, right? So here it will be your induced EMF, and whatever drop you will get here, that will lead to your second voltage, terminal voltage of the transformer.
Yes, sir.
So whatever is induced, that will be just before your current started to drop in the resistance, right? So when drop is zero, it means your terminal voltage is equal to the back EMF or induced EMF, basically. Here, back EMF is the term we use in motors, so here we can call it as induced EMFs, right? So that's why Vp dash and Vs will be same if no current is flowing. We will consider those cases where current is flowing, right? So the first part was to find the equivalent circuit of the transformer. So for doing so, you have to compute this, and if some current will flow, then you have to take care that Is is flowing here, and here Is will not flow here. Ip by A, right? Not Ip by A, Ip into A basically. Ip into N1 by N2. Okay, so basically, I generally do not prefer calling a ratio as A because it is very confusing. I'm very comfortable with referring. So logically, if you are writing primary side current, so you are associating that with N1. So N1 into I1 divided by N2. So that kind of logic I follow generally. So take care of the voltage and current such that power that is being supplied from the source should be equal. At the end of the day, you cannot change the amount of power level, right? So whatever power was being supplied earlier, it will be same no matter how you draw the equivalent circuit. Equivalent circuit cannot change the power of the circuit. So that is a way to verify the circuit whether you have drawn it correct or not. Okay,
Yes, sir.
so great. So just for the sake of answers or values, I will tell you, you verify it on your own. R2 dash is 0. Uh, R2 dash, whatever, sorry, let me just give the value of RC dash, or I think I have already provided it is 60 ohm and 12. So we have computed all the values. You just need to plug in those values there. Okay. So let us focus on the B part. we have to find out the per unit equivalent circuit of the transformer. Okay. Now, when we deal in terms of per unit, okay, we have to decide something as a base value. Okay. That is the definition of per unit. What is the definition of per unit basically? Anyone can say?
It is the ratio of actual value upon base value.
Correct, correct. So the per unit quantity is actual value in any particular unit, in any unit, divided by base value in the same unit. Okay. So we know now here in per unit we have two terms: actual value and base value. Actual value we know it is given or we have computed already for part A. Now base value is something that you have to judge. Okay, you have to decide on your own. So how to compute or how to finalize the base value for the circuit? That is the challenge here, right? So how to define or how to decide what will be the value? And yeah, one advantage with the per unit that you don't need to refer towards any side. You do not need to discrete whether this is from the primary side or secondary side. It will be same throughout the case. Okay, so it doesn't matter which side you are referring. You will just have base value of that side and current value of that side in the case of a transformer. So we will see in this part. So that is very important in this part. So yeah, for that purpose, we need to first decide. Okay, so we are given with the kVA value. So base value of kVA, we can say it will be 100 kVA. Okay, and base value towards the primary side is 8000 volt. Okay, the voltage base value on the primary side will be 8000 volt, and base value of the voltage on the secondary side will be 277 volt. Okay, so I hope you are following. Now, so let me uh, kVA base is already 100 kVA, and voltage base of primary side is 8000 volt, and voltage base on the secondary side is 277. Okay, so here voltage you have to, the base value of the voltage you have to decide every time you are doing the transformer action, whereas the kVA rating will be same throughout the level you are changing, right? So if instead of two turns transformer, it could have been three level transformer, four level transformer, right? So you need to decide the base value of the voltage in each zone. Okay, but kVA rating will be always same. So we will see how does it matter.
Sir, I think base value is nothing but rated value.
Yeah, base value is rated value generally we take if nothing is given or if some loaded condition is given. or if some other value, you can take any value as a base value. See, base value is not something you have to be very sure about it. Okay, base value generally we take rated value as a base value, but you could take any value as a base value. Okay,
Or if you
let's
take any
suppose.
value, then the corresponding other side base value will also change. If the rated,
Yes,
if we have taken the rated value as base value, then if we take the different value as a base value, then other side will also change, sir, in that way.
definitely, definitely. So that is the thing. So that's why we always take rated value. But let's suppose that you are taking uh, on the primary side, 8,000 volt is given as a rated voltage. But you can say that I don't want to take 8,000 voltage as my base value. I want to take let's suppose 80 volt as a base value. 80 volt as a base value on the primary side. So now in per unit, your primary side voltage will be how much? It will be 8,000 divided by 80. So it will be 100 per unit. Okay. So
Sir, here we are considering base value is 80 volt, and what is the actual value? What?
actual value is 8,000 volt, right? Actual volt, actual value was provided in the problem, that is 8,000 volt. But let's suppose you are saying that I will not take 8,000 voltage as a my base value. I will take 80 volt as a my base value. So in that case, you will end up with 100 per unit of primary voltage. Did you get my point?
Okay, then secondary, sir.
Then secondary side, yeah. So what will be the base value on the secondary side? That will be, let us talk in this way. So 80 into 277 divided by 8,000. So that much, I don't know how much it comes out to be, but that much will be your secondary side base value,
2.77.
2.77. So 2.77 here again. And again, you will end up with 100 per unit, but 2.77 is will be your base value instead of
Okay.
277. Earlier it could have been 8,000 base 8,000 volt as a base value of the primary voltage and 277 volt as the secondary voltage, right? Now instead of that, by the logic you have reduced it by 100 times. So now 100 factor of 100 is appearing on the both sides. So it is becoming inconvenient, a little bit inconvenient and confusing for all of us. So to avoid this scenario, we generally prefer rated value as my base value. Did you
Sir,
get my
here
point?
basically we are doing a divide of 100. Like whatever we are doing, we have to do both sides. Suppose we are doing here divide by 100. So 8,000 divided by 100 is 80. 277 divided by 100 is 2.77, right?
Yeah, yeah. For voltage, you have to take care of every side uniformly.
Yes, sir. Yes, sir. I got it.
Okay, so let us not move ahead with this 80 volt of base value. Let us take the rated value as our base value so that it will simplify our calculations. And the primary purpose behind per unit value or per unit system was itself to reduce the burden in calculation. Okay, so let's not forbid that purpose. And so if 8,000 volt as a base value for primary voltage and 277 volt as a base value for the secondary voltage, so it will be per unit, it will be 1 per unit. Okay, so we have decided kVA base 100 kVA as per unit. So 100 kVA we have taken as a base value. Now we are interested in our impedance base. right? Impedance based on the primary as well as impedance based on the secondary. Why both will be different? Any answer for that? Because of course you can see that voltage levels on the both side are changing. And if you remember the Z base value, how do you compute?
Sir, V
Voltage
base by I base.
V base by I base, but here current is not given, and in many scenario you will not be provided with the current value. Okay, so V square divided by KVA rating or VA rating, whatever you want to say. So let me simplify it with writing as a apparent power. Okay, so in
But
this
sir,
case,
I did not got this point, sir.
point V square by S.
Yes, sir.
Okay, so C V square, and this S unit of S is volt amps, right? So ideally you are doing nothing but the voltage by current, but since we are given as a kVA rating on the nameplate of the motor. Okay, so nameplate on the motor you will have kVA as well as voltage. So you don't have the access to the current of the motor when you are purchasing anything or you are given with any problem. Most of them will not have any current rating. So other way to find out the impedance is what? Voltage square by apparent power. So you have to take care of the unit and dimension thing is here. So V square by VA will give you the dimension of impedance. I hope you are aware with this, right? This is very basic. KVA square by MVA you might have studied in the that NPTEL machines course, right? KVA square by MVA I always used to write. So it is what? It is nothing but equivalently voltage by current. Did you get it, Deepak?
Yes, sir.
Okay. So let us move ahead. Z base on the primary side will be voltage square divided by uh, kVA. So voltage square is 8000 square divided by 100 kVA. So if you will compute, it will be base value of the voltage on the primary side and base value of impedance and base value of the impedance on the secondary side. You can calculate it as voltage is 277 square divided by 100 kVA. So it will come out to be 64 into 10 raised to power 6 divided by 10 raised to power 5. It will be 640 ohm. Okay. And the secondary side will be 277 square divided by 10 raised to power 5. It is 0.7672. So these are the base value for primary and secondary side. Now what you have to do, you have to just divide the actual value with these base value in the equivalent circuit what you have drawn, not on equivalent circuit, but not referred to any side, right? The basic the initial equivalent circuit where the primary side was like. So here on the primary side, we had this RP as 5 ohm, right? So now you can straight away 5 ohm by Z base 1, right? And XP was 6 ohm, so 6 by Z base 1. Similarly, RC divided by Z base 1 because it was given with the reference that these values of the parallel branches are referred to the high voltage side. Xm by Z base 1. Any doubt till now, till this point?
Sir, what we are doing this?
We are we are drawing equivalent circuit in per unit. Okay.
Okay. Okay.
So the B part was asked that find the per unit equivalent circuit of this transformer. So there are various ways, but we followed one way in which we found out that here we have to deal with only impedances, right? So what we did, we found out the base value of the impedance from the both side, and we are just dividing the actual values to the base value, and we are getting the per unit values of those elements. So that's what we are doing it here.
Okay, sir. It means if we divide the impedance, we can obtain resistance per unit or reactance per unit.
Yeah, because see, uh, Z is equal to R plus JX. Okay, let us suppose
Yes.
this is actual, R actual, X actual. Now you need Z per unit. For that, you need R per unit plus J X per unit. Okay, and Z per unit, you know that Z actual divided by Z base. So now you have to divide it with Z base. It will come out to be R per unit divided by Z base plus Jx per unit divided by Z base. And eventually it will be, oh sorry, I did something wrong. Yeah, here it will be actual. So actual by base will give you the per unit. So here also it will be actual. Now you can write it Z per unit divided by R per unit plus Jx per unit. And R per unit is nothing but R actual divided by Z base, and X per unit is nothing but X actual divided by Z base. So uh, we identify Z base only, and we divide it all the series elements such as resistance and reactance. So you will get the per unit values of those parameters. Is it clear?
Yes, sir.
Great. So on the secondary side, the reactance was 0.006. Okay, so you have to add divide it by base value of impedance on the secondary side, and next thing is resistance on the secondary side was 0.005 divided by Z base 2. So here don't do the square of Z base, right? Here be cautious. You have to just divide with base value of that element. Any doubt in this part?
No doubt, sir. No doubt. Everything clear, sir.
Very good, very good. So let's move on to the part C where load will come in the picture. Okay. So read the part C. It is saying that transformer is supplying rated load at 277 volt and 0.85 power factor lagging. Okay. Now we have to identify or find out the transformer's input voltage. And once you are able to identify the transformer's input voltage, then you have to calculate the voltage regulation. Okay. Now, what should be the approach for this type of questions? Any comment how to proceed with this part C?
Secondary voltage plus voltage drop is equal to input voltage.
Great, that's all. So secondary voltage plus drop, that's all you have to do, and you will end up with the primary voltage. So, and that primary voltage will be referred to the secondary, right? So Vs plus Is into Zs. If you see this circuit, which was referred to the secondary side, that will be very much helpful here. Okay, so in this circuit, in this network, so in this network, what we will identify here. So this VP dash we have to identify, okay, and this load is given. Now this IS load current is given, okay. Load current is not given, but it is said that this load is supply. Sorry, this transformer is supplying rated load, okay, rated load at 277 volt. So 277 volt, it is saying, it means automatically we can refer that it is on the secondary side. Yeah, anyone want to say something? Okay, so the load is connected on the secondary side. It means we have to refer everything to the secondary side. And so first thing what we need to do, we need to compute IS. Okay, how to compute IS? IS will have some magnitude as well as some phase. Okay, and that phase will be shifted from, if you are assuming secondary voltage as the reference. Okay, so this is a very standard problem which is asked in gate based on the voltage regulation. So what should be your approach to solve this kind of problem? Okay, first you consider any voltage and not any voltage, because you want to save time as well in the exam. So you have to consider the most convenient parameter as your reference parameter. So we will consider Vs as a reference, which will be aligned with angle 0. So this is Vs angle 0. Now, Is is lagging. It is said in the problem that load is lagging by 0.85 power factor at rated load. So it will lag. Is will lag with some phi angle. That phi angle will be reflected here as well. Now you have to identify the VP. VP will be nothing but Vs plus Is into Zs, right? So if you see, you will get some vector here. That angle we will compute in the problem, and that will be your VP. It will lead the Vs by some angle. Let us say delta, because in power system we call this angle as a delta. So this is all we have to compute. So here we are clear with the angle and the reference parameters. Now we have to compute VP dash. So VP dash is nothing but Vs plus Is into Z equivalent. Okay. So Vs is equal to 277 angle 0. Is we don't know. We need to compute Is. Z equivalent We know because we computed in part A, so that we will take it from part A, where Z equivalent is equal to R equivalent plus J X equivalent. Okay, and R equivalent is nothing but R2 plus R1 into N1 by N2 whole square. So let me write it. First, let us compute IS. IS will be how much kVA, 100 kVA divided by,
277.
sorry,
277.
yeah, 277. So it will be how much? 100,000 divided by 277. It is nothing but 361.
361.010 amps.
Yeah, 361 we can round it, and we have certain angles, right? So that angle is point cos inverse 0.85. So that will be 31.8 lagging. So you must take care of these angles when you are dealing in terms of phasor. Okay. So now you are done with IS. Now Z equivalent. Z equivalent is we have computed in the part A, that will come out to be 0.011 plus J 0.0132. Okay, if you compute R2 plus R1 into N1 by N2 whole square plus X2 into N2 by X2 plus X1 into N1 by N2 by N1 whole square. So basically from part A, whatever we computed it here, here we did all those calculations, right? So after referring that equivalent circuit, where did it went? Okay, so if you refer these two elements on the secondary side, that will be after adding both elements, that will be your equivalent impedance. So this value will come out to be this much. Okay. Now you have to feed these values in this equation. Let us call it equation 1. So VP dash will be nothing but 277 angle 0 plus 361 angle minus 31.8. Someone is trying to ask something into Z equivalent is 0.011 plus J 0.0132. Okay, so this is now just the phasor calculation. Okay, I hope you will be able to solve this.
282.892 volt.
282.89. That's correct. And how much is the
at,
angle?
at an angle 0.39 degrees.
0.39. Perfect. It is correct. So that's the VP dash we have calculated. Now to find out the voltage regulation, okay, what is the expression of voltage regulation?
No load voltage minus full load voltage divided by full load voltage.
Great. So VP dash minus VS divided by VS. So it will be, we are concerned only
Yes.
with the magnitude. So we will write 282.89 minus 277 divided by 277. How much is it coming?
2.124 percentage.
2 2.124%, right? So basically it will come out to be 0.021. Okay, so this is the answer for part C. Okay, and this is a standard approach to solve any voltage regulation based problem. Okay, so you just need to take care of phasor calculation very carefully. Otherwise, you might land up doing some mistake, and that might cost you certain marks. Okay, so that you take care. Any doubt in part C? Okay, if not, then let us move to part D here. we need to find out the copper losses and core losses in the transformer under the conditions of part C, means the condition of full load. Okay. So, and in final part, part E, we have to find out the transformer efficiency as well. So, this last two parts will handle the concept of efficiency, right? So, let us, in one question itself, you can observe that you are covering the entire umbrella of single phase equivalent circuit along with its voltage regulation and efficiency. So that's why I preferred this problem, and some professor can frame this problem as a 2 3 gate problems. So gate problems are similar to that, but certainly from the next session I will take, after one this question, I will take based on 3 4 5 gate questions which had been asked in earlier years. Okay, so
Thank you.
yeah, great. So part D and part E is saying that copper losses and core losses we have to find out, and efficiency we have to calculate. So what is the approach here? Any hint? Anything? See, do not deviate. Just that it is not on your screen. Do not forget what is the basic. What is the basic thing you need to do? You have drawn already this circuit. Okay. Whatever current will flow in this RC, that loss corresponding to this current will give you the core loss. Okay. And whatever current is flowing in this resistance, that loss corresponding to this resistance will give you the copper loss. Isn't it simple? In the
Yes, sir.
simplest word, IC square RC is equal to core loss, IS square RS equivalent or R equivalent will be copper loss. So that's what we will do. Okay. I think in part C we have computed IS, that is 361 amps, right? So 361 amps copper loss is IS. Let me first write the expression. IS square R equivalent. So IS is 361 square into R equivalent. We have computed. So that will be 0.11. So R equivalent, we all have computed, and I have provided here somewhere. So it will be equal to 1430.
14.33 kilowatts.
Uh, I think it
14
should.
kilowatts.
Uh, Let me recompute it. 361 square into 0.11.
14.33 kilowatts.
14.33 kilowatt. Okay. 14 point. Thanks for that input. Mm, 33. Okay. Now, uh, this is copper loss. Now, how to compute the core loss? That will be nothing but VP square divided by RC. Okay. So VP we know. VP we have computed. Okay. So VP we have got as 282.89 here. It is 282.89 whole square divided by RC, and RC was nothing but 50 kilo ohm. Okay, so it was 50 kilo ohm,
1.6 ohms, sir.
1.61 watt,
Watt. 1.61 watt.
1.61 watt. Okay, great. So core loss is very less compared to the copper loss. Okay, and now is the time to compute the efficiency of the transformer. Okay, so efficiency, if I want to write, efficiency is nothing but output power by input power. And further, if I would like to extend it, output power divided by output power plus losses. Why I don't want to deal in terms of input power directly? Because we are not given with input power. We will never be given with input power. We will always be given with kVA. Okay. So that kVA and whatever rating is shown in the problem or in the equipment, that that is denoted by output performance. Okay, so whatever kVA or whatever power you will be given or the nameplate value of any equipment, that is nothing but the output parameter. So here output power, how to compute, that is kVA,
kVA into power factor.
kVA into power factor. Great. So power factor we are given with 0.85. Okay, and kVA we are given with 100. So we will do 100 into 0.85.
85
So
kVA.
85 kilowatt. Okay. So we have computed losses. We will plug in those values. Okay. Efficiency is equal to output power, that is 85, divided by output power again 85 plus losses. Losses we have computed 14.335 plus, you know, 1.61. So it will be 0.0.
85.56%.
85.56 percentage. Thanks a lot for computing it. And the efficiency of this transformer is 85.56 percentage. I hope it is clear. This problem is clear to you. Any doubt, any final doubts from any part of this problem, I would be happy to answer. If it is clear, you can give thumbs up. I think you have the access to give thumbs up. You can give thumbs up. Okay, so you have raised an hand.
The solution.
Good, sir.
Sorry?
Everything is clear, sir.
Okay, everything is clear. Great. So
Can
you can
can you
indicate
share
with
this PDF, sir? Can you share this PDF?
uh, I can share this PDF, but I don't know where to share this PDF. I don't have any access. Okay, I will do one thing. I upload this video on YouTube, and in the description, I will give you the link of this PDF. Will that
Sure, sir.
work? Okay,
Yes, sir.
great.
Otherwise, I will post my mail ID in chat box, sir.
Okay, that you can do. You can post your email ID in the chat box, but it will not be accessible to everyone. So I will do that. I will upload in the description as well. Okay, so I think along with you, others also can access, and it will be very convenient for me as well.
Sure, sir. Thank you very much, sir.
You are welcome. So,
Sir, on which YouTube channel you upload, sir?
YouTube channel. Let me post that channel link here. That is nothing but JDS at the rate IITB. So let me post the link to that channel. So I have posted the link to the channel. I hope you are able to access that channel. Okay, so it will be posted there within half an hour. So that's all about today's session. Okay. In the PDF, I will attach one more problem for you to practice. Okay. Let me so if I can. So in the PDF, there will be one problem that you can practice, and you will be very much confident after solving such a long problems, and you can solve all type of problems. Okay. So it's time to wind up the session. Any final doubt related to this session you can ask. Otherwise, we will meet on the next week at the same time.
Sir, efficiency was how much?
Efficiency was 85 point something. Let me confirm it to you. 85.56% is.
Okay, sir.
Okay, great. So thank you very much everyone to joining the session. Have a good night. Bye.
Mm.
Same to you, sir.
Right, sir.
Thank you.
Thank you very much.